All right, let's dive into one of the most mind-bending ideas in all of physics, the Lorentz Transformation. For this explainer, we're pulling directly from Chapter 15 of the book Newton and Relativity. We're going to break down how the universe literally creates different realities depending on who's looking, especially when things start moving really, really fast. So, let's get right to it. So, here's the game plan. We'll meet our two observers and then fire up the relativistic translation engine that connects their worlds. After that, we'll get into the really wild stuff, how this warps space and time, what it means for the universal speed limit, and why at the same time isn't what you think it is. And finally, we'll put it all together to see the blueprint of reality itself. All right, Section 1, two observers, two realities. So, how can a single event be described from different points of view? Let's get right to the core of the problem. Imagine you and I see the exact same thing happen, but I'm standing still and you're flying past in a rocket. Do we measure the same time, the same distance? Well, common sense would say, of course, but physics? Physics gives us a hard no. Okay, to really dig into this, we need a couple of characters. So let's meet Observer O, our cyan friend, who's just hanging out stationary. And then we have Observer O prime, in orange, who's zipping by at a constant speed v. Now, they both start at the same spot when the clock hits 0, but believe me, their views of reality are about to split. Big time. Now, each of these observers has what we call a frame of reference. Don't let the term scare you. All it really is their own personal toolkit for measuring the universe. You know, their own ruler for space and their own stopwatch for time. And that's the whole puzzle we're trying to solve here. How do you translate what one person measures into the language of the other? Next up, the relativistic translation engine. This is the mathematical tool that bridges two different realities. So how do we do it? How do we make that translation? Well, it's not with a dictionary. We need a special kind of engine, a mathematical engine that is the absolute heart of relativity. It's the machine that lets one observer see through the eyes of the other. So here it is, the forward translation engine. You see how it works. You feed it the coordinates from our stationary observer. That's a position, x, and a time, t. The engine crunches the numbers through those equations. And what spits out on the other side? X prime and t prime. That's it. That's the translation. This is the key that unlocks the world as seen by our moving observer. It's how we can see the same event from a totally different high-speed point of view. And what's really cool is that this is a two-way street. We can just flip it around. This is the inverse engine. It lets our stationary observer take the moving guy's measurements and translate them right back into his own reality. The key thing to get here is the symmetry of it all. The laws of physics don't play favorites. They have to work exactly the same for both observers. It's a fundamental rule of the game. Okay, Section 3, warping space and time. Let's see what happens when we run our reality through this engine. We've got our machine all fired up. Now for the fun part. We're going to start plugging in some really simple situations and just watch. Watch as everything you thought you knew about space and time starts to get weird. So, first question. If a clock is just sitting still in one frame of reference, do our two observers agree on what time it shows? Let's really think about that. Our gut feeling, our everyday intuition screams yes, of course they do. But what does our engine have to say about it? And boom! Here's our first bombshell from the engine. For our stationary guy O, the event happens right at time 0. Simple. But look at the math for t prime, the time for the moving observer. See that little vx over c squared piece? Because of that, when O prime does the math, their clock actually shows a negative number. What does that even mean? It means from their point of view, the event has already happened. It's in their past. And just like that, the idea of a universal now that we all share, it's gone, shattered. Okay, so time is officially weird. But what about space? Let's ask another question. If a ruler flies past you at nearly the speed of light, is it still the same length? I mean, how could it not be, right? Let's say a bar is just sitting there in the moving frame. How long does our stationary observer measure it to be? And this leads us to one of the most famous effects in all of physics, length contraction. To our stationary observer, that moving bar is physically shorter. And I want to be super clear here. This is not an optical illusion. This isn't some trick of the light. The actual space the bar takes up has contracted from this point of view. And the faster it goes, the shorter it gets. Wild, right? It's not just space that gets warped. The engine has another surprise for us, and this one is about time. The stationary observer, O,
Looking at a clock in the moving frame, we'll see it ticking slower. I mean, literally, the seconds themselves are stretched out. We call this time dilation. It boils down to this: the faster you fly through space, the slower you travel through time. It's a fundamental trade-off that's just built into the universe.
All right, next up, the universal speed limit. We've just seen that space and time bend, but why? Why does the universe do all these crazy gymnastics? What is so sacred, so important that reality itself has to become flexible to protect it? Well, it's all to protect one single universal constant. So let's imagine a little experiment. Our moving buddy, O prime, is in their spaceship and they fire a photon, a particle of light. For them, inside their ship, this is super simple. Light travels at the speed of light, c. Duh, no surprises. But the real question is, what does our stationary observer on the ground see? And this is the insight that changes everything. Common sense tells you to just add the speeds up, right? The speed of the ship, v, plus the speed of light, c. But that's not what the universe does. When you run this through our translation engine, something magical happens. The math works out so that the speed of the ship, v, just vanishes. It cancels out. Our stationary observer also measures that photon speed to be exactly c. Not c plus v, just c. It doesn't matter who you are or how fast you're going. The speed of light is the same for everyone, always. So, what this all means is that our normal way of adding speeds, well, you can just throw it out the window. The universe has its own special rules called relativistic speed addition. You can see it on the speedometer here. No matter how much you push the pedal, no matter how much speed you add, you just get closer and closer to c. You can inch towards it, but you can never, ever reach it, and you can certainly never break it. It's the ultimate unbreakable speed limit of the cosmos. Moving on to our next section, the illusion of simultaneity. Okay, we've got one last piece of common sense we need to shatter. If the speed of light is truly constant for everyone, what does that do to our idea of things happening at the same time? Can we even agree on that anymore? So let's ask this question. If two lightning bolts strike at the same time for one person, do they strike at the same time for everyone? Imagine you're standing right in the middle of two trees. Lightning hits both at once. From your perspective, you see the flashes at the exact same instant. It was simultaneous. Case closed, right? But what about for your friend who's flying by overhead? Okay, let's look at the setup from the moving observer's point of view, our friend in orange. For them, two photons get launched from points that are the same distance away, on either side. The photons travel inwards, and they both arrive at the dead center at the exact same time. From inside that moving frame, this is a slam dunk. The two launches were perfectly, undeniably simultaneous. But now, let's jump outside and see what the stationary observer sees. From their perspective, the orange target is moving. It's flying away from where the first photon was launched and towards where the second one was launched. Now remember, the speed of light is constant, so that first photon has to travel a longer distance to catch up to the moving target. The second photon has a shorter trip, so for them to both arrive at the same time, there's only one possibility. The photon with the longer journey had to have started earlier. The two events that were perfectly simultaneous for O prime are absolutely not simultaneous for O. Okay, let's tie this all together in our final section, the blueprint of reality. We've seen our everyday ideas of space, time, and even at the same time just fall apart. So let's step back and see what kind of universe we're left with. What does the new blueprint look like? This table, this relativistic translation matrix, really lays it all out. Just look at the disagreements. One guy's measurement of length, the other sees it as shorter. One person's stopwatch, the other sees it ticking slower. Two events at the same time, the other says, nope, one was earlier. They disagree on almost everything. But look at that one row at the bottom, the one thing they both measure to be exactly the same, the speed of light. And that brings us to the final, really profound takeaway. What the Lorentz transformations are telling us is that space and time, they're not the fixed, rigid stage that we thought our lives played out on. They're actually a single, dynamic, flexible fabric, space-time. And this fabric will stretch, it will shrink, it will do whatever it needs to do for one reason and one reason only, to make absolutely sure that every single person in the universe measures the speed of light to be the exact same number. So length contraction, time dilation, these aren't just weird side effects or bugs in the system. They are the fundamental architectural features of reality itself, all built to protect that one beautiful universal constant.